Okay, yep. Proof by induction, FP2. Really cool. Prove that something works for a base case, you know that n equals 0 or 1. This is for integers, by the way. You know, you prove something works for a base case, n equals 0. And then assume that it works for a whole number and show that if it does work for a whole number. Look up the next one. We're going to be talking about Jun12, question 7, AQA. 7 marker. Let's get on with it. Okay. So we've got to prove 3 over 1 squared plus 2 squared plus 5 over 2 squared plus 3 squared times. They've all been times. 1 squared times 2 squared. 2 squared times 3 squared. 7 over 3 squared times 4 squared. And so on. You get the pattern. That's actually got to equal 1 minus 1 over n plus 1 squared. Okay. Induction. That's how we... Why is the camera moved so much? Sorry about this. No. Right. Okay. Very sleek, very professional production, obviously. Let's carry on with it. So this is what we want to prove. For the base case, I'm not going to write it out. You should. I'm not going to write it out. So the base case is the very first case. So 3 over 1 squared times 2 squared. 1 times 4 is 4. So this is 3/4. That bit's 3/4. When n equals 1, 1 plus 1 is 2. 2 squared is 4. 1 minus 1/4, that's 3/4. That's correct. That's what you write down. I'm not going to do it. That's what you write down. That all works. Okay, the base case is correct. Now we assume that this works for some integer n equals k. So assume, again, we're writing this out because it's not really true. Okay, so assume for n equals k that it works. I'm gonna have to. I'm gonna have to write that up again. 1 squared times 2 squared plus 5 over 2 squared times 3 squared plus all the way, actually, up to 2k plus 1 over k squared times k plus 1 squared. And we're going to assume that that works. So assume that that equals 1 minus 1 over k plus 1 squared. Now, what I need to show is that this works, that if this does work, so we assume this is true, if this works, that this will work with n equals k plus 1. This will work for the next integer along, and that's what proof by induction is all about. So I want to show that all of this up to k plus 1, up to n equals k plus 1. So I want to show for n equals k plus 1 that 3 over 1 squared plus 2 squared plus 5 over 2 squared is times 3 squared. Now all the way, I'm going to include that term. That's going to be the second to last term this time. And the last term is going to be this, but with k plus 1 in it. So 2 lots of k plus 1. Hope I'm not going into the light. No, it's okay. Plus 1 over, I think I am going into the light, but I'm going to read it out. Hopefully you know. You should. K plus 1 squared. K plus 1 is k plus 2 squared. And I want that to equal this, but with n is equal to k plus 1. So I want that to equal 1 minus k plus 2 squared. Okay. Now in order to show this, I'm going to use my inductive hypothesis. I'm going to use my assumption. So all the way up to the second to last term, I'm going to swap that for 1 minus 1 over k plus 1 squared because it's identical. This bit here is identical to what I want to show all the way up to the second to last term. So I'm going to swap that for, so just thinking about the left-hand side of this here, trying to get it to equal 1 minus 1 over k plus 2 squared. So the left-hand side up to the second to last term is 1 minus 1 over k plus 1 squared. And I've got to add on the very last term, plus 2 lots of k plus 1 plus 1 over k plus 1 squared times k plus 2 squared. And I want that to equal this thing here. What's the same, what's different? That's the usual game we play when we want things to equal to each other. So I've got this one here, and I've got this one here. That's great. I'm going to leave that. Not going to touch it. Okay. So this thing here, I want to equal 1 over k plus 2 squared. Not sure how that's going to work at the moment, but I can see that this has got a k plus 1 squared in it, and this has got a k plus 1 squared in it. I'm going to be able to get a common denominator of these two fractions, k plus 1 squared times k plus 2 squared. Let's try that now. So that equals 1 minus, if I make this a common fraction, I'd have to multiply top and bottom by k plus 2 squared over k plus 1 squared times k plus 2 squared plus, don't need to do anything to that denominator, that's already how I like it. 2 lots of k plus 1 over k plus 1 squared times k plus 2 squared. Okay, I'm going to go back up to the top of the board. I'm going to get rid of my assumption. To do that, I am going to leave the top line on now. Okay. Now these fractions have got a common denominator. I can combine them. And because I've got a takeaway here, I'm going to leave one takeaway at the beginning, so it matches up with this. So what have I got? I've got one takeaway, and then in a big bracket, put an equal sign here. So this would be k plus 2 squared, but then because I put the takeaway here inside a bracket, I need to make this minus as well, so it works. So minus 2k plus 1 minus 1, and that's all over k plus 1 squared times k plus 2 squared. When you're doing this, you should be looking at what you want to get to and thinking about how I'm going to get there. I know at the moment I'm going to need a factor, hopefully, of k plus 1 squared to cancel out with this. Let's see if I get that. K plus 2 squared expanded, k squared plus 4k plus 4, take away 2k is what I get from expanding that bracket, take away 2, take away 1 over k plus 1 squared times k plus 2 squared. That equals, so k squared, 4k minus 2k is 2k, and then 4 minus 2 minus 1 is plus 1 over k plus 1 squared times k plus 2 squared. And I can see now I've got exactly what I want because I've got the factor of k plus 1 squared on the top. This is 1 minus k plus 1 squared is that whole thing over k plus 1 squared, hello, k plus 2 squared. I hope you could see all of that on the board. When I do this cross out here, I've got exactly what I wanted for part A. That's 7 marks there. It's pretty good. Part B. Yeah, part B will be done using an inequality. I'm not actually going to do it on here. I'm going to give you a little hint. Let me know if you can do it. If not, get back to me. We can go through it in future. That's all right. Find the smallest integer n for which a sum, which you worked out to be this, differs from 1 by less than 10 to the minus 5. 10 to the minus 5 is 1 over 10 to the power 5. So that's 1 over 10, 100,000 probably. So to do this, when is this less than or equal to 1 minus 0.00001 or something like that? Swap around the inequality, get this n plus 1 squared from the bottom, multiply it so it gets up to the top. You should be able to solve it. It's a quadratic inequality. Like I said, let me know if you can't do it. There's no shame in that. It's alright. Cool. Okay. I hope you've been able to see all my algebra there. As always, let me know if you've got any questions, queries, comments, anything like that. Alright.